Hello, everyone. I wanted to finish out the rest of the chapter on acids and bases. This will include the completion of the discussion related to the acid or base properties of salts, as well as a example of a weak base calculation as has been requested. So we'll start out with some new information and then we'll talk back to what we had talked about at the end of class and look at some examples for these cases of acidic or basic properties of salts. So the new idea here is looking at the properties of metals dissolved in solution. If we have a highly charged metal ion that is small, so it's a cation, this will actually affect the pH of the solution. It will affect the acidity of the solution. To preface this, I need to remind you that if we have group 1 or group 2 metal cations, those are pH neutral. So we have already basically talked about that because those are the counter ions of the strong bases. And they don't have a high charge, right? They have a charge of +1 or +2. The reason why this is true for more highly charged metals is because of the way that they're hydrated. And we'll introduce a little bit of that right now, but it will become a bigger concept in a later chapter we will be getting to this semester. Here we're showing what that looks like. When we say they're hydrated, what that means is that the metal ion is surrounded by water molecules. So we're showing that here. We're showing the way let's say an aluminum ion would exist in solution is not just an aluminum with a +3 charge, because that high charge is going to attract some electrons. So what ends up happening is that it is surrounded by these water molecules that have, some electron density on the oxygens. So we end up with this complex that still has a +3 charge, but is surrounded by 6 water molecules. Now, it's generally better to spread out charges. So what then ends up happening is one of these water molecules might donate a proton to a water molecule that's not part of the complex in order to minimize the charge on the complex as a whole. So the complex will go then from a +3 charge down to a +2 charge by basically distributing part of the positive charge to this unsuspecting water molecule that ends up not even part of the complex, but ends up as a hydronium ion. So when this happens, we are making this solution more acidic by creating hydronium ions. And again, that's so that we can spread out that +3 charge into a +2 and a +1, which is more stable. So that's what happens there. And that's why when we have charges of +3 or more on metals that are dissolved in solution, those solutions become weakly acidic for that reason. So I'm going to go back, and this is kind of the final piece of the puzzle, classify these salt solutions as being acidic, basic, or neutral. So there's a few categories here. If the salt has counter ions of a strong base combined with counter ions of a strong acid, we'll have a neutral solution. So we're looking at some examples here. So what you could do here to kind of figure out if that's what you have is you take what you're given, break and turn each piece into an acid or base, and ask yourself, is that strong or weak? So for this one, we break it into sodium and chloride. We would then look at, okay, sodium hydroxide, is that a strong base? That is a strong base. hydrochloric acid, is that a strong acid? That is a strong acid. Okay, so because of that, these are neutral. So both of them are counter ions of strong acid or strong base. If you look through these other two examples, I'm not going to go through these in the same detail, but you would find the same thing. We have counter ions of strong acids and strong bases put together. Those will be neutral solutions. The next example we had is if we have the counter ion of a strong counter ion of a strong base, and the anion is the conjugate base of a weak acid. Okay, in this situation, we'll form a basic solution. So the conjugate base of a weak acid is what is making these basic solutions. Okay, so we see, okay, sodium is a weak, or I'm sorry, sodium is the counter ion of a strong base. It's not going to do anything. Okay, so counter ions of strong things don't do anything, is essentially what we're saying. The fluoride ion is the conjugate base of hydrofluoric acid. Okay, so that's going to do something. Okay, so when it is the conjugate of a weak acid, that ends up being what affects it. Okay, so this one would be basic for that reason. I'm not going to go again through these in the same detail, but for each one of these, they are going to be basic. There is a conjugate base of a weak acid, which is what is making them basic. And then here we're looking at the kind of opposite example of that. If the anion part of this is the conjugate base of a strong acid, that doesn't do anything. But the cation is the conjugate acid of a weak base that will do something. So conjugate acid of a weak base does something. Because it does something, that part will then be acidic, whereas the part that is the counter ion of a strong acid does nothing. Okay, so this one will be an acidic solution. And then finally, the one we just talked about, if there's a highly charged metal ion, and the counter and the anion portion of it is the conjugate base of a strong acid, will have an acidic solution. So here we're saying, okay, nitrate is the conjugate base of a strong acid. It does nothing. Okay, so this one is doing nothing. This one is making it more acidic. Okay, so we'll have an acidic solution. I'm going to briefly talk about this because I'm sure some of you are thinking about it, but it's not something I'm going to dwell on a lot this semester. So you might be thinking, well, what if you have a mix of both? What if you have something that is the conjugate base of a weak acid along with something that's the conjugate acid of a weak base? What if that happens? Then you have to look at it in a bit more detail. So here we're looking at an example of NH4F. So the NH4 is the conjugate acid of ammonia, which is a weak base. The fluoride ion is the conjugate base of hydrofluoric acid, which is a weak acid. So then what we do is we compare, okay, which one of those is the bigger effect? In this case, hydrofluoric acid is a stronger acid than the ammonium ion. And how we would figure that out is we would just compare them. So we would look up Ka of the ammonium ion, look up Kb of the fluoride ion. And then because the Ka of the ammonium ion is larger, then we know what the trend will be. And so the solution is acidic. So you're comparing them to decide which is which. Again, I'm not going to focus on this one too much. There may be a homework question on this, but it's a little bit more complexity, so I think we don't need to necessarily have it on a quiz or exam. Okay, so what we want to do is we want to get a bit of practice. So what I would recommend is you pause the recording right here, and try to go through and decide for each of these. I will give you a hint. I'm not going to tell you which one, but there is one of these, which is that mixture of, okay, we have to go look things up. You can, if you want to, just when you get to that one, say, okay, we would have to go look things up. I'll tell you what it is, and I'll tell you what the right answer is when we get there, but don't feel like you have to look that one up. So go ahead and pause things, try these out, and when you come back, I'll tell you the answers. Okay, so for the first one, we have sodium and we have bromide. Sodium is the conjugate of a strong base. Bromide is the conjugate of a strong acid. Neither one of these do anything. They don't do anything at all. So this is a neutral solution. Okay, so the first one is neutral. For this one, the lithium bicarbonate, we have lithium is the conjugate of a strong base, so it does nothing. Bicarbonate is the conjugate of a weak acid. Okay, so it will do something. This one will do something. So this one will be basic. So the conjugate base of a weak acid is going to make it somewhat basic. For the next one, NH4Cl, we have NH4 plus. The ammonium ion is the conjugate acid of ammonia, which is a weak base. And then chloride ions are doing nothing, right? Because they're the conjugate of a strong acid. So this one has the bigger effect, so it will be acidic. Okay, next one, ammonium cyanide. This is the one you can kind of skip. You can't just look at it to make that decision. You would have to look up the values of Ka and Kb in order to decide. And I'll tell you, if you want to try it out, you'll end up finding that it is basic because the cyanide has a greater effect. The cyanide ion has a greater effect than the ammonium ion. And that is by comparing the values of Ka to Kb, and you might have to convert some of those from Ka to Kb in order to do that comparison. Again, you don't have to focus too much on these ones where you would have to look it up. I want you to be able to do the ones where you can recognize when you have counter ions of strong acids and strong bases and make the decision from there. Next one, we have iron 3 chloride. We recognize iron 3 has a positive 3 charge, so it has a high charge. That will tend to make it acidic, and that the chloride ion is the counter ion of a strong acid, so it does nothing. So this part makes it acidic, this part does nothing. So this would be an acidic solution. And then the final one, lithium nitrate. Lithium is the counter ion of a strong base. It does nothing. Nitrate is the counter ion of a strong acid. It does nothing. So nothing happens here. This one is also neutral. Okay, so just an example of how to make those decisions. You will need to do this on the homework, and it could come up on the quiz or exam as well. Okay, I promised you we would look at another example of a weak base calculation. And what I've decided to do here is to actually use your homework as an example of this. So this will get you through one of your homework questions if you haven't done it already, sort of, because it won't be exactly the same as your question necessarily. It might be similar, but it won't necessarily be exactly the same. So the question here is determine the hydroxide concentration of a 0.24 molar ammonia solution. And then there's a follow-up question, determine the pH of a 0.24 molar ammonia solution. Okay, so these are both asking about the same thing. And there's actually something that will be very useful about the way this homework question is set up. And that is the answer to the first part, so part A, will help you answer part B. So when you work on this, do the part A first. If you don't have it right, don't go on to part B until you get part A right. Okay, so just be aware of that as you're working on this. One of the things that we need to do to solve this, actually, before I get into too much detail here, I would recommend that you go ahead and try to solve this. Or have a plan. Actually, don't get too far with this because we'll see it's going to change a little bit. But think about what your plan would be. This is the only information you're given in the question. So maybe pause, think about what else you would need to solve it, and then keep going. So the other thing you will need is you will need the value of an equilibrium constant. In this case, because we're looking for the hydroxide concentration, we probably want the value of K sub B. Okay, so we'll have to look that up in a table. And let me go ahead and show you the table, and then we'll move ahead and solve the problem together. Okay, so on the table, we have ammonia, which is the solution we were looking at. And we see that Kb is 1.76 times 10 to the negative 5. Okay, so I'm going to write that down as some information we will need to solve this problem. Okay, you might have heard me writing there, and then what I'm going to do, I'm going to go ahead and transfer to the document camera, and we will do the rest from there. Okay, so let's go ahead and continue. You'll notice I wrote down the value of the equilibrium constant for the Kb for the base up here, as I was talking about that. Also, there's one other thing I want to show you here. So if you've already solved this based on what we looked at, I want to point something out. This is a different concentration than what we saw earlier. And the reason for that is that your homework is going to randomize some of the numbers to make sure that you're doing it, and it has an algorithm for solving those. And I had a different screen capture in what I put in the PowerPoint than what I have here. So what you had seen before, I believe, was 0.24. This is 0.20. When you do exercise 16.89, it might be one of those, it might be the other, it might be something different altogether. So don't just take my answer here and plug it in and assume it will be correct. You need to follow the process for it. Also, be aware that if you have already paused and solved this, I'm going to get a slightly different answer, but you should feel confident in the method of how to get there, right? So the point isn't the number itself. I mean, that is important, but it's the method you use to get there that is what ultimately you need to understand in order to do well on these kinds of questions. We need to start with our rice table. So let's go ahead and do that. So the reaction, we're not given a reaction, we have to know what that reaction is. So we do know we have a base, so we have NH3, and so we're going to have the standard reaction of a base with water to form hydroxide ions. Okay, so we have hydroxide, and then we have NH4+. Okay, so that's the first step. And then we have the initial amounts. So initially we are given the concentration of the base. So that concentration is 0.20. We don't care about water. These both start at approximately 0. And we're pretty much always going to do that again, unless you have a question that says specifically you have this and this. So you would have essentially two concentrations provided, or you have something that's a polyprotic acid. Okay, the change. 90% of the time, the change is going to be from reactant to product. We can tell for sure by seeing that the products are both 0. So we have a minus x plus x plus x. Okay? And then we have equilibrium. Okay, so at equilibrium, we have 0.20 minus x, x, and x. Okay, so this should look very familiar. This is kind of how the Rice tables typically end up working out. And so we can kind of know, okay, this is what we thought it would be, this is what it is. And then we make the assumption we make 90% of the time, which is that this is approximately equal to 0. Now I will tell you, there is at least one homework question where you cannot make that approximation. And your hint for that is, if you look at the whole question, it's going to ask you where did you not make the approximation. So that is telling you, okay, I'm going to have to do this the hard way at some point when I get to that question. But most of the time we can, and we can for this one. Okay, so what we do, we take the equilibrium amounts, put them back into the equilibrium expression. I'm going to start by writing the this in terms of the symbols. So we have our two products. And divided by the reactant. Okay. And then we put in what we have. So we have x squared divided by 0.20. And then what we're going to do is solve for x. And I think I'll go ahead and do this in a few steps. So we'll have x squared is equal to 0.20 times 1.76 times 10 to the minus 5. So let me actually go ahead and do the math on that. Okay, so we have a calculator here, 1.76, and then exponent 5 negative, okay? And then times 0.2, and we get that number. Unfortunately, my calculator is not automatically putting it into scientific notation, so I'm going to count there. There's 1, 2, 3, 4, 5 zeros. So that's going to be 3.52 times 10 to the minus 6. Okay, so you might, if your calculator does the same thing, let me actually move that so you can see it. You might have to do that kind of a math on there. And then again, unfortunately, I'm kind of running out of some space here. I'm going to put the x down here. So what we're going to do there is take the square root of that. So square root button right there. And that's our answer. Again, I'm going to put that in scientific notation. So there are 2 zeros. So we'll call that 1.87 times 10 to the negative third. So that is x. And if we look back in our table, we have, I'm going to minimize that calculator now. If we look back in our table, we found X. X is equal to the hydroxide concentration. So that's 1.87 times 10 to the minus third. That is our concentration of hydroxide. Okay, so that is what you would put in there as your answer. Again, let me remind you, when you are doing your homework, when you get to 16.89, your answer is probably not going to be 1.87 times 10 to the minus third, because you probably have a different concentration of the ammonia. But hopefully you can see how you would use the same method to find what that is for your particular question. All right, so that's part A. For part B, we're finding the pH of that solution. It's the same solution. So we've already found part A. Make sure you get part A right before moving on to part B, because your answer for part A is going to determine your answer for part B. Now, when we were doing a weak acid solution, we would take the concentration of hydronium and just put it into the pH equation. We have an extra step here, in this case, because we are starting with hydroxide instead of hydronium. So what we're going to do is we're going to start by finding the pOH. So the pOH is the negative log of that concentration. Okay, so let's go ahead and bring our calculator back up. So I've left the number in there, so we can go ahead and do the log. And then we switch the sign, because it's the negative log. So that is equal to 2.73. And then we can say, okay, we're looking for pH. So pH equals 14 minus pOH. Okay, so we're going to say, okay, we'll put a negative on there and add 14. So that's going to be 14 minus pOH. And we get this number, 11.27. Okay, so that's what we would put in as our answer. Now, whenever you find pH, always a great idea to check if it makes sense. Okay, so what you're looking for here is, when you're finding pH, should you expect a number bigger than 7 or less than 7? We have a basic solution. We have a base. We would expect pH to be greater than 7. pH is greater than 7. Okay, so that's kind of how we know we're on the right track. If we had accidentally just gone and done pH here, thought this was finding the pH, and we wrote 2.73, we should recognize, okay, that's a number less than 7. I probably didn't do that right. What else do I need to think about? And then move on and do this step. Okay, so that's how we would do that one. I think there's actually on this one a part C where you might be finding pOH. So that one is a little bit out of order, so they're not necessarily always going to be on the homework in exactly the order of one feeds into the very next one, and for A and B that works out. Just be aware when you see this one, you will also have that part C. So that is the video for this chunk of the chapter, and hopefully it helps you to do well on the homework assignment.